Okay, I'll get started if that's okay. Um, so we're going to continue talking today about manifolds, and we're going to just say a few words to finish up the basic notions about manifolds, and then talk about other constructions involving manifolds. And I want to apologize for anybody who's seen basic um, differential geometry before. Those things that we are going to go through that you will have seen before in a more classical sort of finite dimensional setting, and we're going to be talking about those in the infinite dimensional setting, and they'll look just the same. And so I apologize because that'll be boring. Um, but one should prove that everything is the same, and so that's what we're doing. Okay. Right. So, last time so the time before last time, we had talked about the basic structure of manifolds, charts, and atlases, and all this kind of thing. Then we spent some time last class talking about examples, and today I want to sort of just finish that discussion up and talk about special classes of manifolds. And then the classes here are going to be distinguished by where the chart maps take their values. Okay, so let's let uh, M. So this is a set with a differentiable structure. And a CR differentiable structure. Okay. All right, so M is again, this is about where the charts take their values. Okay, so M is a finite dimensional manifold. If each admissible chart, so let me say it this way. So if for each admissible chart, U phi phi V phi, the vector topological locally convex topological vector space V phi is finite dimensional. Okay, right. So and so I'm not there's going to be a bunch of words that I'm going to be repeating here, and so I'm not going to reproduce them. I'll just replace them with quotes. So M is a an n dimensional manifold. Okay, and n here is going to be a non-negative integer. If, okay, and then for each admissible chart, U phi phi V phi V phi is n dimensional. Okay, excuse me. So finite dimensional does not mean n dimensional for some n, um, because you can have situations like this. So you can have, here's a manifold. So the manifold is going to consist of a point a circle, and a sphere. Okay, so it's just the union of these three things. Right, and so each of these things is, so this one is um, zero dimensional. This one is one dimensional. And this one is two dimensional. Okay. Um, but there's no reason whatsoever, according to our definition of manifold, that we can't just take our set S to be the union of these three things. Okay. And so S is the union of these. Okay, so S is certainly finite dimensional. Every chart takes its values in a finite dimensional vector space, but it doesn't have a fixed dimension. So the thing you notice here is that these different components of this finite dimensional manifold, the zero dimensional component, the one dimensional component, the two dimensional component, those are disconnected, right? So each of in other words, what I'm saying is that S is a union, or the manifold is a union of its various dimensional components, and so that will always be the case. So you're never going to have a case where one component is one and two dimensional. They're always going to be separate, and that's and by separate I mean disconnected. And that's just because if you have a mapping between two Euclidean spaces, which is a homeomorphism onto its image, like a chart map is, then those two Euclidean spaces have to have the same dimension. Okay. Things are more complicated in infinite dimensions, but in finite dimensions, you have this sort of decomposition into components of various dimension. And I should say, uh, um, finite dimensional does not even demand that there is a finite n, so that every chart takes its values in some Euclidean space, or some, sorry, n-dimensional vector space, or some vector space whose dimension is less than or equal to n. So for example, you could take this construction that I've drawn here, and you could just go and so here I basically have a point. Here I have, let's say, S1. Here I have S2. And you could just, take countable unions of SNs. Okay, that will still be a finite dimensional manifold, but there's no sort of bound on the dimension of the components. All right, so you can get these kind of fairly uninteresting, but kind of pathological behaviors. All right, so just be aware of what the definition says and what it doesn't say. Okay. Typically when you're working with classical introductory elementary differential geometry, you sort of make a blanket assumption that you're working with manifolds of some fixed dimension. But as I say, there's no reason why you should do that. Okay. M is a Banach manifold. If Okay. And so again, it's going to be, for for every admissible chart, U phi phi V phi, V phi is a Banach space. Okay. And so just remember that a complete normed space, that's what a Banach space is. Okay, so this includes, for example, the finite dimensional case. Is every finite dimensional normed vector space is complete. Okay, but it includes also infinite dimensional examples. You could think about something more general than this. You could think about not Banach manifolds, but manifolds whose for which VP is not necessarily a Banach space, but a normed space. Typically in any applications of infinite dimensional differential geometry, one works with Banach manifolds, not just manifolds modeled on normed vector spaces. Okay, but certainly for the point of view of just saying things that are mathematically reasonable, there's no reason here to sort of focus on the Banach space case. Okay, that the interest in Banach space comes from applications. And so you'll notice that there's really a dearth of applications and examples in this course, and that's because applications and examples are hard. And I'll see how time goes as we go along, and maybe we can say some things at the end of the course about some kinds of applications. But applications are difficult of infinite dimensional differential geometry. And that's a regrettable part of the theory, but it's true. So you can't just, sort of do 10-minute examples. Those don't exist, or non-trivial 10-minute examples. Okay, so similarly, you have Hilbert manifolds. So the model spaces V phi in this case are Hilbert spaces. So excuse me, complete inner product spaces. Okay, and then there's, we didn't talk about this when we talked about locally convex spaces, but locally convex, so this is kind of a breakdown of, three different kinds of locally convex spaces: finite dimensional, Banach spaces, and Hilbert spaces. There is a zoo of kinds of locally convex spaces, and when you study the theory in detail, you will run into that. And so, in principle, you can define, a classification of manifolds based on each of these categories, and some of those things may be interesting, some of them may not be. One that is interesting um, is so these are all the examples so far are normed, and so this is the first sort of case of a kind of manifold which is modeled on a space that's not normed. So it's what's called a Frechet manifold. Okay, if, and so again, for every admissible chart, U phi, V, U phi, phi, V phi, V phi is a Frechet space. And we didn't talk much about Frechet spaces, so let me say a few words about it now. So i.e., a complete, so part of the definition of Frechet is complete. So a complete metrizable, and I'll say a few words about metrizable because again, I didn't when we talked about locally convex spaces. I should have, but I didn't. There were things that I didn't want to talk about at that time because I wanted to get to talking about calculus, and so we skipped over quite a lot of stuff in locally convex spaces. And one of the important ones that I could have covered but didn't is the notion of metrizable. So I'll talk about that now. So a complete metrizable locally convex space. So, okay, so let me do that in an organized way with an aside. So a locally convex space is metrizable if um, there exists. So obviously metrizable, you imagine it has to do with the existence of a metric. Of course that's true. But a particular kind of metric. So metrizable if there exists a translation invariant, and I'll say what translation invariant means. So a locally convex space V O. Okay, if there exists a translation invariant metric, D. Let me say what translation invariant means. So it has uh, um, the definition that when you translate the arguments, you get the same thing. So explicitly, that means D of V1 plus V, D V2 plus V is D of V1 V V2, right? So if you translate each of the arguments of the metric, it doesn't change um, the distance. Okay, and this of course is true for every v v1 v2 in v. Okay, so that's what a metrizable locally convex space is. So one can show, and it's shown in the course text. One can show that V is metrizable if and only if um, its locally convex topology can be defined by a countable collection of seminorms. Okay. All right, so we know that every locally convex topology can be defined by some collection of seminorms, and if you can choose that collection to be countable, countable could be finite, right? And in the finite case, it essentially means one. So uh, um, let me discuss this a little bit in detail here because like I said, I think I wish that I had talked about this when we talked about locally convex spaces, and since I didn't, maybe let me do that a little bit more carefully now. So examples. Um, norm spaces are metrizable. And this is obvious because the locally convex topology is defined by a single seminorm, which in fact isn't just a seminorm, um, but it's a norm. Okay. Um, okay, so Banach spaces and Hilbert spaces, those are examples of metrizable spaces. Um, if the topology of uh, V, let's consider the finite case. And so what I said was the finite case essentially amounts to the normed case. And so let me explain why that's true. If the topology is defined by a finite collection, let's say P1 up to PK of semi-norms. Then the topology is also defined, so the same topology. So it's also defined by a norm. And so I have this finite collection P1 up to PK of semi-norms, and I can combine those into a norm in various ways. And I'm going to write down 3 ways. And then I'll sort of tell you, the general sort of rule for combining these things, these finitely many semi-norms into a norm. So I could go P infinity is so P infinity of V is max P1 of V, Pk of V. Okay, so that's one way of building a single norm from that finitely many semi-norms. You could go P2 of V. It's J equals 1 to K P J. So let me maybe call these ones Q so P1 doesn't coincide with my P's that I already have. So Q infinity and Q1. Okay, and then for example, you go Q2. Okay, and so in fact, if you take any norm for Rk, the k-dimensional Euclidean space, and feed as the entries into that norm the vector of semi-norms, that'll also define for you a norm. Okay. So in other words, what I'm saying is the case of finitely many semi-norms, the topology being defined by finitely many semi-norms, that's really just normed, is what I mean to say there. And so really the distinction is normed, meaning one semi-norm, which is actually a norm, and countably many, but not finitely many. So those are the 2 interesting cases. So and how what is the normed are the normed cases somehow special amongst the metrizable ones? Well, they are, and so you can characterize them relatively easily. And so, in fact, you can characterize them not just among the metrizable locally convex spaces, but amongst all locally convex spaces. So let me just say this is a fact, and it's not a hard fact to prove. And again, the proof is in the course text. Okay. So a locally convex space VO is normed if and only if V possesses a bounded convex zero neighborhood. Okay. So certainly, if it's normed, It possesses a bounded convex zero neighborhood, namely the unit ball in the norm. Okay, so that one implication of that, if and only if, is clear. Excuse me. The converse implication is proved by the following argument. You suppose that you have a bounded convex zero neighborhood. What you do then is you show that the Minkowski functional for that bounded convex zero neighborhood. So we talked about the correspondence between semi-norms and neighborhoods, and the way we did that was through Minkowski functionals. And so for a bounded convex zero neighborhood, you can show that its Minkowski functional is a norm. Okay, good. Okay, so that's just a little aside there about locally convex spaces that and I mainly was interested in talking about this because this class um, of manifolds is important. The ones where the model space is a complete metrizable space. Okay, many interesting examples fall into this class. Okay. So I wanted to say some things about what metrizable meant. Okay, good. Um, okay, good. Um, all right. So this is my, sort of some kind of a classification of manifolds, finite dimensional, Banach, Hilbert, and Frechet. There are definitely other interesting classes, but that requires digging into um, locally convex spaces in a kind of depth that we're not going to do. Okay, good. So now let's talk about submanifolds. All right, so that's all I'm going to talk about with basic the basic theory of manifolds. Now we're going to start talking about things you do with manifolds, and the first thing that we'll talk about are submanifolds. And so, submanifolds have uh, um, the usual kind of property of things that are sub-things, and that is a submanifold should be a manifold. Okay, so we're going to define a certain kind of subset of a manifold, which inherits from the space in which it sits its manifold structure. Okay, so we go like this. So I'll give the definition in words, and then I'll draw the picture. Okay, and the picture tells the story. Right, so let R. Right. Okay, so a subset S of M is a submanifold, and so let's say that it's a so frequently one doesn't specify the regularity, and one just assumes the regularity of the submanifold is the same as that of the manifold, but maybe it's not, and so I won't be careful um, uh, about including this prefix. Okay, so a subset of the submanifold if for each x in M, oh, sorry, not M, S, okay, there exists a chart. Okay, and so whenever I say chart, I mean admissible chart. So I will follow the world and not carefully say admissible. So I'll just assume that whenever I talk about a chart, it's admissible with a manifold structure. So U phi phi v phi. Okay, and a sequentially closed, and so we'll talk about why we need sequentially closed. Subspace. Okay. When I say subspace, so in topology, people very often talk about subspaces, and in topology, when you say subspace, you mean subset. And in locally convex spaces, you're working both with vector spaces and topological spaces. So typically, you want to be careful when you use the word subspace. So when I say subspace here, I mean a linear subspace. Okay, so a sequentially closed subspace W phi contained in V phi. Okay, such that okay, so phi chart applied to the points that are in the chart domain, of course, and are also in S, okay, is equal to um, the points in the image of the chart domain intersect W phi. Okay, so we call U phi phi V phi a submanifold chart. And so the subspace W phi is also sort of included there. So when you talk about the submanifold chart, this is the chart um, for M, okay? And then when you include this piece of data here, that's where S gets included. And so the whole thing is described by this triple along with W phi. And so I'm typically going to write all that together. Okay. So when I want to specify a submanifold chart, I will give the full sort of collection of data. Okay, good. So what's the picture there? All right, so submanifolds, you should think of as, in your mind's eye somehow as being, smooth surfaces of some kind. Okay, like the n-dimensional sphere sits inside Rn plus one. That's, an n-dimensional submanifold of the n plus one dimensional manifold Rn plus one. Okay, so that's the picture you should have in your mind. All right. Okay. And we'll talk a bit about that example later, particularly in the one-dimensional case where you can be very explicit about it. Okay, but let me draw the picture here in generality. Okay, so I have a manifold M. Okay, so M. Then I have a submanifold, and so by my drawing is M is a two-dimensional thing, and so the submanifold somehow is really can only be a one-dimensional thing. So this is S. Okay. And so I take a point X, according to my definition, I take a point X in S. Oh, and I didn't say it, although it's always so X, of course, has to be in U phi. Okay, so it's a chart about X. All right, so the definition says, so maybe let me draw it in red. I have a chart U phi about the point X. Okay, and then I have U phi intersect S is this thing. Okay, because that's part of the definition. All right. And then phi maps me into v phi. Okay, so this whole thing, let me not draw it there. So v phi is the locally convex space in which phi takes its values. Okay, and then sitting inside v phi, I'm going to have a subspace, w phi, okay, which I will put in blue. Okay. Okay, so this is w phi. And then the chart phi maps u phi into some subset here, which is phi of u phi. Okay. And so the definition just says that the points in u phi, which are also in S, are mapped onto this subspace W phi. So the idea is that in this chart, it takes this, in my picture and in your mind's eye, takes this curvy thing, S, and it kind of flattens it out. Okay, in the same way that a chart itself takes the manifold and flattens it out. So now I have a manifold and a subset, and so the point is I can find a chart for M, which doesn't just flatten out M, it flattens out S. Okay, so it maps it into a subspace like this. Okay, so that's the picture you should have in your mind. All right. So let's look at some elementary examples. All right. So first of all, there's this example is sometimes newcomers find the example confusing because it's too easy. It's degenerate. Okay. Um, so let's let V be a locally convex space, and let's let O in V be open. Okay. So we've seen that V is a manifold because it has the single chart just given by the identity map. All right, so we think of V as being a manifold defined by the atlas. So an atlas is a bunch of charts, and so the chart here is going to be a single chart, V with the identity map. Okay, so that's the atlas. And so my charts, I should be consistent with my charts. So it's right. So a chart is a U phi, a phi, and a V phi. All right. Okay. So we claim that the open set O is a submanifold. Okay. So what's the definition? The definition is that I need to do two things. I need to find a chart about any point in O, okay? And I need to find a sequentially closed subspace. And so this sequentially closed, we'll see why we need that. It's not going to show up for a little while, but we'll see why we need that. But in any case, you need to find a sequentially closed subspace W phi so that this is true. Okay, so let's just see how we go about that. So indeed, let's just, show that the definition holds. We let X be in O and take the chart So the chart we take is the chart we already have for V, the identity map, and the sequentially closed subspace W. Well, let me not call it W phi. Let's just V. Okay. So I just take the subspace to be the whole thing. Right. Okay. um, and so clearly, right. So what's the thing we have to verify? Okay. We have to verify that. Okay. Clearly, phi of, right? So what's the definition? The definition is I take the right. So the definition is I take the intersection of the chart domain with the submanifold, and I show that that is the intersection of the image of the chart domain with the subspace W phi. Well, that's just obvious. Okay, so phi of V intersect, so V is U phi, S is O. Okay, so this of course is just O, um, is O, which is equal to uh, phi of O, okay, because phi, so phi is the identity map here. Okay, so it's just so obvious that it hardly bears writing down. Okay. So open subsets of locally convex spaces are submanifolds of the locally convex space. Right, good. So that's not an interesting example, but it's an example. Okay, more generally, if M is a manifold, any open subset of M is a submanifold. Right, so this is again trivial. It's just slightly less trivial than the preceding example, but you end up with equivalently, sort of dull things that you have to verify. Okay. Um, okay, but you should go sit and do that just to make sure that you understand the definition and how to use the definition in this kind of degenerate case. Okay. In any case, such submanifolds are called open submanifolds. It's just another way of, you can say open set. All right, so it's an open set, but you call open sets when you want to say that these have a manifold structure, you call them open submanifolds. Okay. All right, so those are two general but rather dull examples. Let me give you a very specific but still easy example, but at least one which isn't as degenerate as those ones. Okay. Let's look at S1. We've looked at S1 before, and I gave you, we ground out specifically an atlas for S1 to show that it was a manifold. Now I'm going to grind out submanifold charts for S1. Okay. Okay, so S1 in R2. Okay, so what's the definition? So the definition is you want to find you want to find a particular kind of chart, okay, which flattens out your submanifold into some subspace of the model space. Okay. All right. So I need to find. So let me write down clearly what I need to find. Need to find for each x1, x2 in S1, a chart, U phi. And so the chart here is going to be for the manifold M, and the manifold M is R2, and so I'm going to take my model space to be R2, okay, because R2 is a two-dimensional manifold, and a subspace, and so it has to be sequentially closed, but linear subspaces of R2 are, because R2 is finite dimensional, are closed, and so are sequentially closed. So just a subspace. W phi in R2 such that phi of U phi intersect S1 is phi of U phi intersect W phi. All right, that's just the definition of a submanifold. Okay, translated into this specific problem. Okay. All right, so you have to think this is not often the way you verify that something is a submanifold, but I'm doing this just to show how the definition works. Okay, usually there's easier ways to show that things are submanifolds, especially in finite dimensions. In infinite dimensions, things are more complicated. Okay, all right, so let me just choose a point here. X1, X2. Okay, so what do I need to do? I need to find a chart. I need to find a chart about that point for R2, okay, which and so when you think about what's going on in this picture here, okay, so I have this subspace, W phi, okay, and in this picture, I've drawn W phi and I've kind of drawn this axis here. And that certainly makes sense for R2. It doesn't necessarily have a lot of good meaning for in infinite dimensions because this picture kind of suggests something that I'm not saying. It kind of suggests that there's a complement to W phi inside V phi. And I'm not assuming that, but I include this thing just to draw the picture, okay? Because the picture would look kind of dumb without having some axis to indicate that it's a vector space. But in R2, this does make sense, all right? So this is going to be sort of one coordinate of my chart, and this is going to be the second coordinate of my chart. And so if you think about what I need to do here, I need to find coordinates for R2 so that one of the coordinates is 0 along the circle. Okay. Okay, so well, certainly if you find a set of coordinates for R2 so that one of the coordinates is constant on the circle, then you can subtract that constant to make it 0. Okay, so there's an obvious choice of coordinate for R2. Um, um, which is where one of the coordinates is constant on the circle, and that is polar coordinates. Okay, so polar coordinates are r theta, so r is equal to 1 along along S1. So that's going to be how I build my submanifold chart. Okay, so define U phi is going to be So I'm now going to write down polar coordinates, and I'm going to, change the polar coordinates a little bit. The polar coordinates, you usually write them as, r theta. Okay, here we're going to write the coordinates as theta r. That's obviously not a very interesting change. But what we're going to do is we're going to write the coordinates as theta r minus 1 because we want to take the radius coordinate to be not 1 along the circle, but 0. Okay. All right. So good. Polar coordinates. So what's the domain of polar coordinates? Well, you need to just, sort of have a domain, a subset of R2 where, the angle theta is well defined, and, the radius r to any given point is well defined. So certainly you need to exclude the origin because the angle of the origin is not well defined. Okay. Um, And if you remember, the charts need to map onto open subsets of some locally convex space. You can't just throw away the origin. As we'll see, you need to kind of throw away some kind of line there that when you take it away from the domain makes it open. And so what we're going to do is we're going to omit that line and this point. Okay, so it's going to be whoops. R2 take away the set of points x 0 where x is less than or equal to 0. Okay, so it's R2 take away that line including the origin. Okay, that's the domain u phi. Okay, v phi is going to be R2. Okay, so we're talking about polar coordinates here, which are r theta, or for us, it's going to be theta r minus 1. So there's two of them, so R2. And phi of x, y. Okay. Okay, so it's going to be polar coordinates. So theta, like I said, I want to name the first coordinate. Sorry, let me just think if I actually said that right. Yes, that's right. Sorry. Good. I want to put a tan of x, y. All right, so we talked about a tan when we talked about putting coordinates on the circle. So a tan just returns this angle, okay? And it takes two arguments because if it takes two arguments, then it can resolve the angle from pi to minus pi, okay? And then r, okay, so root x squared plus y squared minus 1. Oops, not like that. Like that. Okay. Okay, so let me draw the picture here in case it's not blindingly obvious at this point. So what does this coordinate chart do? So I'll draw the picture and the picture will verify that this thing is in fact a submanifold chart. Oh, and I need my W phi. W phi is going to be the x-axis. Okay, so E1 is the first basis vector, so I'm just taking the span of the first basis vector. Okay. All right. All right, so here's R2, and I have a map here, phi. Okay, so so let me draw also let me draw the chart domain. Let me do it in red because that's what I did before. So I omit the line along with the origin. So u phi is going to be all of this stuff. Okay, so it's u phi. And what does this map to in R2? Okay, so we're going to call this theta and this r. Okay, so this is theta and r. Okay, so r is really not quite r. It's the usual r minus 1. Okay, because I want it to be 0 on the circle. Good. Um, so what are the values of theta for points in u phi? Well, it's the strip from minus pi to pi, right? Because the angles take all values between minus pi and pi. Okay, so it's going to be theta um, like this. Okay, so pi and minus pi. All right, so and R here, what will the values of R be? Well, R is going to be positive, right? So that's the usual R. Oh, sorry, R is going to go from, the usual R goes from 0 to infinity, so this R goes from -1 to infinity. Okay, so the range for R looks like this. Okay, so the image of this thing under phi looks like, oops, looks like that. Okay, does that make sense? Okay, good. And so now we just note that this that the circle intersect u phi. What does that get mapped to? Well, that gets mapped to the set of points where r is equal to 0 and theta goes from minus pi to pi. Okay, so the blue thing here is u phi intersect s. Okay, and that gets mapped to this thing. Okay, so that is phi of u phi intersect s, but that's also equal to, and this is the submanifold condition, it's also equal to phi of u phi intersect w phi. Okay, and the fact that that's an equality, just that's the verification that this thing is a submanifold chart. Okay, so there's a trivial example, but one which is at least has some stuff going on in it, unlike the previous examples, which were kind of degenerate. Okay. All right. So again, more interesting infinite dimensional examples to verify explicitly that they're examples. So for example, what's true, but it's not necessarily so easy to verify. Um, we had this thing that we looked at in detail last time. The unit sphere in a Hilbert space. This is a submanifold. Okay, and you can verify this explicitly by building a by taking the coordinates that we talked about last time and making some minor revisions to them. Uh, but I'm not going to do that. Okay, and there's easier ways to verify that things are submanifolds, and we're not going to talk about this right now, and possibly we'll talk about it a little bit more detail later. So let me just say remark. One does not normally verify the submanifold property directly. Directly, but uses something like, if you've seen it before, good. If you haven't, then again, maybe we'll have time to talk about this later. I hope so, but I'm not sure. But I'll mention it here anyway. Uses something like the implicit function theorem. And the implicit function theorem is kind of a classical thing in calculus. It's also kind of a classical thing in calculus in normed spaces. But unfortunately, um, the implicit function theorem, uh, so if you know what it is, good. If you don't, then what I'm about to say doesn't have a whole lot of impact. Implicit function theorem does not generally hold in locally convex spaces that are not normable. Okay. Um, and so coming up with things that are submanifolds in infinite dimensional spaces that are not normable, that can sometimes require some work. All right, because you don't have a simple tool like this implicit function theorem that I'm talking about to use. Okay, good. That's so submanifolds. Okay, let's talk about products of manifolds. Um, sorry. Let me not do that right now. Let me instead show that submanifolds are manifolds. I should do that. Okay. Um, so if M is a CR manifold, and R is the usual R, and S is a submanifold, then any collection of submanifold charts. Okay, so we've talked about what submanifold charts are. All right, so any collection of submanifold charts for S that covers S. Okay, so so for example, in this picture here, we had a submanifold chart, but it didn't cover S. So what we'd have to do in this example is we'd have to make another submanifold chart that here we had to omit this point on the circle. So we would choose, sort of a rotated version of polar coordinates, which would exclude this point on the circle. Um, um, and that way you would have two submanifold charts that covered S. Okay. So, but generally speaking, we know that around every point we can find a submanifold chart. So we're just going to assume that we can cover we know that we can cover S with submanifold charts. And I'm just saying that if you take any collection of submanifold charts that covers S, defines an atlas according to the following construction. Okay, so I need, for each submanifold chart, what I'm going to do is I'm going to define a chart for S. Okay, right. Okay, so given a submanifold chart, U phi phi V phi W phi. Okay, so that's all the data we need for a submanifold chart. So given a submanifold chart like this, we define a chart, okay, for S. Okay, and it has kind of the obvious definition. Okay, so the domain for the chart is going to be U phi intersect S. The chart map is going to be phi restricted to the restricted to that. And the um, locally convex space in which the charts take their values is obviously going to be W phi. Okay. All right. So for each submanifold chart, okay, I define a chart for S like this. And so I need to show that it's a chart, and I need to show that two different charts that intersect satisfy the overlap condition. Okay, so oh, and so before I prove that, let me finish the statement here. So moreover, the manifold topology S is agrees with the induced topology from M. Okay, I'll be getting up for a second. I'll be back in 5 seconds. Okay. All right. So this is not a hard proof, but it is kind of annoying. And really, it's just a question of assembling the symbols in the only way possible, basically. Okay, so let's begin. Um, so first, we're going to make a construction um, which also will address the last assertion here. Okay, so first we show that phi restricted to U phi intersect S. Okay, so I need to make that a little bit nicer. Okay. Okay, so this is a map from U phi intersect S into, so what's the, so phi of U phi intersect S, the definition of a submanifold chart is that that is phi of U phi intersect W phi, and that is contained in W phi. Okay, we're going to show that this thing is a homeomorphism onto its image. Okay, and so what that will do is that will make sure that the topology on here is going to agree with the induced topology on here from M. Okay, because what this shows, so the topology of W phi is the induced topology from V phi, the big space, where the chart, this space, okay? And so the topology on here comes from V phi, and so the topology on here also comes from V phi. And so what this shows is this actually shows this. Okay, so let me prove it, and then I'll try to summarize why what I just said is true. All right, so we're going to show that this is a homeomorphism onto its image. Okay, when I say something's a homeomorphism onto its image, so this, first of all, it has to be a bijection, or it has to be an injection, okay? And then it'll be a bijection onto its image. That's one thing that needs to immediately be true. And it needs to be continuous. That's one part of homeomorphism. Okay. And it needs to be open. And so open means that if you restrict to the image, the inverse mapping is continuous. Okay. So you need to show that it's continuous and open. All right. So let's prove continuity first. So continuity means that I take an open set in the image. So the image is this thing. So I take an open set in here, and I need to show that its pre-image here is open. Um, and I should be careful about what the topologies are here. Okay. Um, the the topology for U phi intersect S is the induced topology from M. And the topology for the image, so the image is phi of U phi intersect W phi, is the induced um, the induced topology from V phi. Okay. So forgive me while I jump up here for a second to the picture because I think the picture maybe makes this clear. So U phi intersect S, all right? So clearly that sits inside M. Okay, so this is going to have the topology induced from M. Okay, here, this thing sits inside V phi, and so this thing is going to have the topology induced by V phi. And notice that the manifold topology on this set, and this is the definition of the manifold topology that we talked about last time, the manifold topology on this set is exactly the topology inherited from this as an open subset of V phi defined by the fact that phi is a bijection. Okay, so the manifold topology on here is exactly the topology for which open sets here get bijectively mapped to open sets here. That's the definition of the open set up here. All right. Okay, so that's the statement that I'm going to prove first. Okay, so let. All right, so this is a bit technical, but this is again one of those things where you have to say a lot of stuff to prove something that's really quite simple. And so the simplicity of what's going on, and the simplicity of what's going on is really just the picture that I just kind of drew. Um, up here. But now to turn that all into symbols is it's a bit of writing. Okay, but keep the picture in mind. Okay, so let. So I need to show that the pre-image of an open set here is open here. Okay. So let O in oops in um, right. In phi of U phi intersect W phi be open. Okay. Now that's open in the topology from V. Okay, that's what I said here. Okay, so open in the induced topology means that there's a larger subset in V whose intersection with this thing is equal to O. Okay. Um, and because this thing is already open, I'm going to assume that my larger subset is actually contained in this open set. Okay, so let O prime be contained in phi of u phi. Okay, so remember, this thing now is open in V. That's the definition of a chart. Okay, so I'm going to choose an open subset of this open set. Okay, be open. And such that um, uh, O is equal to O prime intersect W phi. Okay? Right? So maybe sorry, I'm going to scoot back up here again and I'm going to draw what I'm doing on this picture. Okay, so what I'm doing is I'm working just down here. So I'm taking an open subset of this intersection. Okay, so that's going to be something that looks like this. Right? Then I'm saying choose an open subset of V phi, and I'm going to choose it small enough so that it's contained in here, whose intersection with W phi is O. Okay, so O prime will be some bigger thing here, and O will be an open subset of W phi. Okay, so that's what's going on there. Okay, so then, oops. Phi, okay, so phi, right? So again, it's just super duper tedious notation. So I need to show that the preimage of O in here under this mapping is open in here. Okay, so it's O intersect U phi, so restricted to U phi intersect S inverse of um, O, okay, is equal to, um, okay, so what's it going to be? It's going to be uh, phi restricted to U phi intersect S inverse of O prime, okay, all right, and this is going to be phi, sorry, it's going to be by definition, right? So when it takes the preimage here, it's going to map it into there. Okay, so it's going to be U phi intersect S intersect phi, oh, sorry, phi inverse of O prime. Okay. Um, why is that? Okay, so this comes from the fact that I'm essentially inverting phi on this set, and so this mapping is a bijection from here to here. Sorry, from here to here. Okay, and I'm just taking the pre-image of that, and so I just get this. Okay, but then I have the points in O prime. Okay, and those are going to be, I take the pre-image of those under phi as well. All right. But this thing is open. But O prime is open in M. And so this thing is equal to the intersection of this with an open subset of M. And so therefore this intersection is open in the induced topology on there by definition of the induced topology. Okay, so U phi intersect S intersect phi, sorry, phi inverse of O prime is open. in U phi intersect S in the induced topology from M. Okay, so as I said, none of this is hard. The notation is requires sitting down and sort of filtering through what, a horrible sequence of symbols like that means. Okay, so but there's nothing conceptually difficult there. This is all just definition. It's all just because phi is continuous, and the definition of the induced topology is that it's open sets in the induced topology are intersections of open sets in the larger space. All right, so very simple, but notationally it's heavy. And so similarly, so I won't repeat the argument. It's rather the same. Just um, I with arguments like this. Very often, they prove themselves if you just write down symbols that make sense. But that takes a little bit of thought. But it's just if you can keep track of domains and codomains and write down mappings applied to sets that make sense, then the proof reveals itself to you. But it does take some time to write these proofs down carefully. Okay. So similarly, one shows that phi restricted to U phi intersect S is open. Okay, and I should say open onto its image. Okay, and it's exactly the same kind of argument, except you're going the other way. All right, so this proves the last part of the theorem, and we're also going to use that here. Okay. All right. Um, good. So now we need to. So what does this show? So notice that this verifies that. Um, so we need to verify that our potential charts, okay, the things which we've proposed to be charts, which are these things, okay, we need to prove that they're charts, okay? So what's the definition of a chart? Well, you have some subset of the manifold, and in this case, the manifold is S, so certainly this is a subset of S. Um, you need to have some locally convex space in which the chart map takes its values. We do, W phi. And then we need to show that the image of phi um, in W phi is open. And so we're going to, the things that we just proved actually give us that for free. Okay. So note this verifies that phi restricted to, because this is our chart map now. One of the tedious things here is the chart map is cumbersome. That's the chart map. Okay. It's that whole thing. Okay. This Oh, and let me maybe instead write it like this. The image of this, okay, um, is equal to phi of U phi intersect W phi is open in W phi. Okay, and that's one of the things we need to be true for our proposed charts to be charts. Okay, so thus U phi intersect S phi restricted to U phi intersect S. Oh, sorry here. I'm. Oh no, sorry. Yeah, it's okay. No, I made a mistake, but I think it's all right. Um, W phi. These are charts. Okay, so we verified that these are charts. Okay, so what remains to be done is to verify the overlap condition. Okay, so I'm going to do that now, since to postpone it till next time would just mean I'd have to restart too many things all over again. So I'm going to go a few minutes over. I hope if you need to go, then go. Um, but I'll finish this up. Okay, so finally, we verify the overlap condition for two charts. Okay, so the two charts are going to be, so again, cumbersome notation, U phi intersect S, phi restricted to U phi intersect S, W phi, that's one chart. And then the other one is U psi, psi restricted to U psi intersect S, and then W psi. Okay, so we verified the overlap condition. Okay, so the overlap map here is going to be, so what's it going to do? So it's going to map, all right? So it's going to be psi restricted to, so this is the chart map in this case. So again, it's tedious notation, but it's a simple enough thing. Okay. So remember that the overlap maps are sort of psi composed with phi inverse. It's just these maps now are cumbersome. Composed with phi restricted to U phi intersect S inverse. Okay. So this is going to be a map from, okay, phi of U phi intersect W phi into psi of U psi intersect W psi. Okay, right. All right, so we need to show that that map is um, um, uh, CR. Okay, if the overlap maps for the manifold, if the manifolds of class CR, then its overlap maps are CR. So we need to verify that these restricted ones are also CR. Okay, so now since M is of class CR, okay, so psi composed with the inverse. Okay, so this one is the sort of clean one. All right, so this goes from phi of U phi to psi of U psi. Okay, so this thing is CRF. Okay. All right, but what I need to do is I'm going to use this map now to define this map. And it's very simple, obviously. Okay, so this thing goes from here into here. Okay, but I'm interested in not going from here into here. I'm interested in going from this intersection into this intersection. So certainly, if I take a point in here, okay, and I take its image under the overlap map, definitely it lies in here. Okay, because both of these things, okay, um, So let me not write it down. Let me just say it in words. If I take the pre-image of both of these things under the chart map, that lies in S. Okay, so both of these things are images of points in S, and so therefore this map will indeed map this one into this one. It's the CR-ness that I'm concerned about here. Okay, so to show that um, uh, psi, sorry, restricted to U psi intersect S composed with phi restricted to U phi intersect S inverse is CRF. Okay. We note that um, these maps, so let me say that the iterated derivatives and these are the things we defined as DJ. Okay. Okay. Are so let me maybe say it this way. We note that there, no, the iterated derivatives DJ are just the iterated derivatives for the full overlap map. Okay. But restricted to curves. So remember that when we calculate these directional derivatives, okay, and maybe I should carefully, I should say directional because that's makes it a little bit clearer. Okay, because when you take the directional derivative, you take a directional derivative of a curve, and you just restrict yourself to curves that lie in W phi. Okay. All right, so are just the iterated directional derivatives for U psi restricted to curves in W phi. Okay. And so we know that those iterated directional derivatives exist and are continuous. Okay, so the full, the uh, um, restricted um, iterated directional derivatives are then continuous as mappings into not W psi, but V psi. Okay, so let me explain that. Okay, so what I'm doing is I'm taking this full mapping here, okay, and to calculate the directional derivatives of this thing, which maps this into this, okay, I'm going to restrict myself to directional derivatives along directions in the W phi direction, okay? So that's one thing that I'm doing. And to calculate that, I'm just taking the full mapping, not just the restricted mapping, but the full mapping, and just restricting the directions in which I'm differentiating it. Okay, and I'm restricting the directions to be in V phi, or sorry, W phi. All right. Now I know because this thing is CRF that those directional derivatives are going to be continuous as mappings into the full space V phi. Okay, but what I want is I want the directional derivatives to be continuous as mappings into W phi. Okay. Okay, and this goes back to something that we proved, and I can understand if you forgot it. That if you have, so I'll maybe just remind you of the result here. Okay, in yellow. Okay, so we had the situation where we had um, um, an open subset of U and a mapping phi from O into W, which was a subspace of V. Okay. And what we wanted to know was we wanted to know what are the conditions which ensure that if I know that phi is of class CR as a mapping into V, then it's also of class CR as a mapping into W. Okay. And the condition was the W had to be sequentially closed. Okay, so that's where the sequentially closed business comes from. Okay, and I will summarize that by just saying, so since, oopsie, since W psi is sequentially closed, okay, these, okay, and I'm getting tired of writing this, these restricted, iterated, directional derivatives continuous as mappings into W psi, not just V psi. Okay, so that's that's what, and so that shows that the overlap mappings for the submanifold charts are class CR. Okay, so that's a tedious bit of stuff there, but it's just notationally tedious. And it's one of those things that's maybe worth sitting down and understanding all the symbols there, um, because differential geometry has a lot to do with working with charts. And this is a really good exercise in working with charts. So I think it's not a stupid idea to go through and understand this sort of avalanche of symbols that's involved in this proof. Okay. All right. So next time we'll start with talking about products, which I started and then realized I'd forgotten to talk about finish talking about submanifolds. So next time we're going to talk about products, then we're going to talk about mappings between manifolds. So these are generalizations of mappings between locally convex spaces. Okay. So unless there's questions, we'll finish up there for today. Okay, I'll see you next week.